Hi everyone. Today I wanted to make this video about this paper that really caught my attention. I've been reading it very carefully in the past few days. I wanted to make a quick overview about some concepts that are necessary for the paper and the paper itself. It's a very interesting paper because it mixes ideas from LLMs and Rex's work. This is not the first time that a paper tries to use concepts from LLMs. Actually, natural language process has been very connected with recommendation systems, but at least some ideas from recommendation systems actually come from NLP. So this is not the first time, but there are a lot of very interesting concepts that appear in this paper. So I think it's worth it to mention. So this paper is called LLM2Rec. It was published a few weeks ago on Archive. Um, So I wanted to discuss some of the ideas from a mathematical and technical point of view. I'm not gonna talk about the implementation or the details of the code. The code was published as well by the authors. The repo is available in GitHub, so you could check it if you are interested. But here we're gonna discuss about the ideas and basically the technical heart of the paper. So before diving into it, I wanted to discuss some ideas that are necessary to understand the heart of the paper. The first one is sequential recommendations. And basically here I want to talk about how we can model recommendation problems using the natural sequential structure that user actions have. Right. So, for example, if you go to Netflix, then you watch different movies, there is a natural sequence on those actions. And that sequence is actually a very good way to understand the behavior of the user. So it's pretty common to model recommendation problems using that sequential structure. So we will discuss a bit about it. After that, we will talk about these concepts that are extremely important, probably the most important concepts in transformers, in LLMs right now, right? That are the concept of attention, self-attention, causal attention, and bidirectional attention. You might have heard a lot about these things, so we'll discuss some mathematical details of them. In the third part, there is one concept that comes from the contrastive learning world. It is called unsupervised sim CSE. It's actually a very simple idea to understand, so we'll discuss this because it's a very important part of the paper. And in the last part, we will put everything together and we will talk about the LLM2Rec. So this is the first time I do this kind of video, so I will try to not mess up a lot of things. So please be patient if there are some problems or some details to improve. So let's start with sequential recommendations, right? So if you think, for example, in all the things that you do in some e-commerce, for example, I don't know, in Amazon, if you are looking for some specific item, there is a very natural sequence of actions, right? So in this case, we have Lily that she is looking for some shoes, then different, I don't know, these jackets, right? So there's a very natural way to see this, right? She first looks to this, then she moves to this, then to this, to this, to this, to this. And all those kind of things actually create this sequential structure. If you are looking, for example, in chronological order, then you could come up with something like this, right? It's a sequence of actions that is telling us how she was looking for the item that she was interested in, right? And we could see that like this as well in the case of IB. So this is pretty natural, and if you think about it, most of platforms, most of the things that actually perform some recommendations have this kind of a structure, right? In social media, Amazon, Netflix, whatever, right? there is some very natural way to model the problems as a sequence, right? Of course, not in all the cases the chronological order is the important one. Probably there might be some cases in which we are interested in a different order, or probably there is a more natural order to induce these sequences, right? So, but in general, we could think of like we have some order. The most common one is the chronological one, and based on that, we could create some sequences, right? So, in mathematical terms, let's say that xu, which is the sequence of x1, x2, xn, be the actions the user u, right, has performed in order. Again, this order uh, depends very heavily on the application that you are working on, right? But we can think of safely, at least in sake of this application, that this is just the chronological order. What was your first action, then the second one, and so on, right? So essentially, we want to predict what the user is going to do next, right? So we want to predict the next action xn plus 1 in the moment, in the near future, based on all the history of the user xe, so xu. So we want to predict, in other words, the action xn plus 1 based on all the history, and we could call this the recommendation of the moment n plus 1, right? Pretty simple, pretty intuitive, right? But this is not, for example, how very simple recommendation models work, like, I don't know, matrix multiplication. Matrix multiplications uses like interactions between users and items, and then we have this big matrix, and we want to create two matrices that represent the users and the items representations. I mean, some kind of embedding based on that. So if you see those kind of recommendations, there's no any order included in how those models work, and that's not the case here. And there is a pretty reasonable reason why we want to recommend recommendations problems like this. So let me make this comparison, right? So let's think for a moment in the problem that LLMs are trying to solve, which is the next token prediction, right? In next token prediction, basically you have a sequence of tokens, words, right? And you want to predict the next token based on all the history that you have, right? So this is the next token, and this is the history of tokens that is not called history in this concept, in this context. This is called context, actually, right? So this is exactly what LLMs are trying to do, right? This is the training goal of the LLMs, right? They're trying to predict the next token based on the context that you have, right? And think about the problem that we just created here, right? So in sequential recommendations, the parallel is pretty clear, right? We have a sequence of actions. Here, actions mean, again, this depends a lot on the context. Action can be a click, can be a purchase, can be whether you watch some item or not, some movie or not. But this is, in general, some kind of interaction between users and items, right? So we have this sequence of actions, and what you want to predict is the next action based on all this history, right? So the parallel is pretty clear, right? You want to predict next action, and this is the history, the user history, right? So it's pretty reasonable to think that we could apply some ideas that work pretty well here in these kind of problems, right? Of course, there's a lot more structure in how a text is created, basically, because we have grammar rules, we have a lot of things that language has. But in general, the ideas can be applied kind of, I mean, I wouldn't say literally, but you could translate most of the ideas that work here in this scenario, right? So of course, this is more, I mean, there is more noise here because humans are not completely predictable, right? But in general, there are some ideas that there are some ideas that you could apply. So this is why we want to model recommendation problems using this sequential structure, because if we model the problems like this, we could apply some ideas that we know pretty well from this NLP world. And actually, this is something that, I mean, this has been done a lot in the past. So recurrent neural networks have been used a lot in recommendation problems, but of course, recurrent neural networks have the problems that we know about the vanishing of the gradients and all those kind of things, right? So transformers is a very natural choice if we want to improve this kind of models, right? So this is essentially how we model the problems, the recommendation problems using sequences, and why we want to do that. Okay. So after that, let's move on to a very important and very well-known concept of attention, right? Specifically, let's talk about self-attention, causal attention, and bidirectional attention, okay? Again, probably you have heard a lot about these kind of things, about attention. Let's discuss a bit of how this works under the hood, and uh, you will see why this is important in our case, right? So what's attention? Well, attention is the backbone of modern transformers. You know pretty well the name of that famous paper from 2017, right? Attention is all you need. And what does attention do? Basically, attention measures the relative importance of an element of a sequence comparing to the other components. Basically, attention is trying to tell you this part of the sequence, how important is comparing to the other elements of the sequence, or not necessarily the same sequence, right? We could compare that word or that token comparing to the other sequence, right? So, for example, in this diagram that we have here, notice that in this part we have a sentence in English, how was your day? And we have in this part a sequence in French, right? So this is a very classic example of translation problem, a sec-to-sec problem, right? And here, based on this sequence, you can compute how important the different parts of this sequence is for each of the words in this one, right? And this is the general concept of attention, right? This can be applied to different sequences. For example, we have the cross attention that can be applied to different sentences, but that's not um, this is the general concept, but we are especially interested in self-attention. Self-attention is nothing more than attention applied to the same sentence. So, for example, in this case, we have two different sentences, one sentence in English and the other one in French. But here in self-attention, we want to compute the attention scores based on the same sequence, right? Uh, it's nothing more than that, right? If we understand attention, basically we have already understood self-attention. So we have something like this. So I wanted to, um, I mean, this is a sequence in Chinese, right? Chinese, I guess. I hope so. But essentially, this is the same sequence, right? You have the same sequence here, you have the same sequence here, and you have the attention scores. So for each token, basically, you have how important this token is for the other tokens. So if you observe this token here and this token here, the score attention is very high, right? And this is the kind of things that we compute using attention. And this is extremely important. Turns out that this is actually one of the reasons why modern transformers are so powerful, because they can understand which pieces of the sequences are the important ones, right? So this improves a lot the efficiency and also the performance of the models, right? So this is essentially like the idea behind transformer. Let's discuss a bit about mathematically what this is doing under the hood. So let's suppose that we have a sequence x1, x2, x1 be a sequence of tokens. Here I'm referring to tokens, but it's, in general, these tokens can be any kind of object we want to model, right? I mean, this is tokens in the concept of NLP, right? But for example, in the case of Rexes, we will also have some sequence that can have a different structure, right? But tokens is in general a small piece of information, so we could talk this. We could think about these things as if they were tokens, right? So we have this sequence of tokens, right? And the first step in the transformer architecture is basically create some embeddings representation of the tokens. Those are embedding layers. They are learnable embeddings. So for each of these tokens, we could create a sequence of embeddings, right? So this is the sequence of tokens, and from that, we can get the sequence of representations or embeddings, and we could represent it as E1, E2, EN. So these are embeddings. This works like, I mean, this is just an embedding layer that creates this embedding. This is just a lookup table. Here we are not passing through. I mean, we could do that, but in general, we could think about these embeddings as the embedding layer. That's the first step of transformer or other models, right? So we have these representations of the different tokens, right? And we could stack them together into a matrix like this, right? So based on that, we could create the matrix E just as all those embeddings stacked, right? We stacked embeddings and we could create this matrix A. So basically what we have here is the matrix of all the representations of the sequence that we have, right? And here's the point about uh, attention, right? Attention has three different pieces or ingredients that are very common, right? So we can get the matrices Q, K, and B, right? These are the famous matrices, as Q is the embedding E, right? This matrix MQ is the multiplication of this matrix, the representation of our tokens, multiplied by this matrix. We will discuss a bit more about these matrices. The matrix K, the keys, is A multiplied by this, and B is A, and sorry, this is B, and this is K, right? So this is called the keys, the query. This is called the keys, and this is called the values, right? These are the three uh, elements of the attention mechanism, right? What about these matrices, right? So these matrices are actually some learnable, right? These are learnable matrices, right? So notice that under the hood, the queries, the keys, and the values are nothing more than linear transformations of the initial representations of the embeddings. Of course, these are learnable, so we don't know the weights of these matrices beforehand, but at the end, no matter what the weights are, at the end, what we have here is just a linear transformation of E, and the same here and the same here, right? But these are learnable matrices of the mechanism, right? So these are the matrices, and then the output of that attention layer is computed as the output. I'm pretty sure you have seen this several times, right? Is the queries multiplied by the keys divided by this term plus, well, let's call this M, sorry, M this, just to not, I mean, yeah, this matrix here and these matrices are different. So let's call it in a different way. And then this multiplied by the values, right? So at the end, notice that here what we are doing here is computing the dot product between the queries and the keys, right? So these are actually the attention values that are necessary for the model to work properly. Those are basically these kind of things that we have here, right? So what are these guys? So this M, this is pretty important. This is the mask, and this is extremely related. Notice that we haven't discussed yet about causal attention and bidirectional attention. We're just talking about attention. This is not even self-attention. I mean, yeah, this is self-attention, but we haven't discussed about causal and bidirectional attention, right? So this is the mask. This guy here, let's put it in this color. This guy here is just the dimension of E1, right? So this is basically the dimension of the embedding layers that we have for each of the tokens, right? So this is the final, the output of the attention score. You are computing the dot product between the queries and the keys. So basically you are getting these values, you are normalizing them by the dimension of the embedding layers, and then you are applying softmax, right? Just so, I mean, just to make everything to sum up to 1, right? And then you are multiplying this by B, right? So this is in general like the representation of B. This is just some values that are multiplied by B. So the output of this is just a new representation of this element B, right? So, I mean, yeah, we have discussed about self-attention so far. This is great, but what about causal attention and bidirectional attention that are actually the important parts of this? Notice that in this case, let's forget this M for a moment. If we compute this, we are computing these values for all the pairs in the sentence, right? No matter the order, we are computing these values for all the elements in the sequence, right? For example, here, for this token, I have attention numbers for all the different tokens along the way, right? But that's exactly the difference between these two concepts, right? And let's think for a moment about decoder-only models like GPT, for example. In GPT, you're trying to predict the next word, right? So it makes a lot of sense that you only have to use the elements that come before the token that you are that you are trying to predict, right? You're not allowed to use future tokens. You should only use tokens from the past, right? So this is where it appears the causal attention idea. So essentially the causal attention means, hey, since you're trying to predict next work, you're trying to predict what's coming next in the future, you're definitely not allowed to understand the relationship between these kind of tokens. So, for example, this is the first token, so you are not allowed to use tokens in the future. You are using these tokens, you are only allowed to use tokens up to that token. After that, you are not allowed to do that, right? So, for example, if you want this token in the future, you are not allowed to do that. And this is exactly what causal attention means, right? Causal attention means you can also use tokens in the past, right? To understand, you can also use those tokens to create the attention numbers, right? And you can imagine bidirectional attention is the opposite of that, right? Well, not the opposite, but in this point, you don't have that constraint. Basically, here you're allowed to use all the pairs of tokens that appear in the sentence, right? So this is bidirectional attention, right? So in this point, you are allowed to use this, for example, and then compare with this token and compare with this token, which is the last one, and this is completely allowed, right? So as I told you, causal attention is actually the mechanism that is used in decoder-only models like GPT. Bidirectional attention is very used in BERT-like models, right? You're trying to encode your sentence, and if you're trying to have this representation of language understanding, then bidirectional attention is a very good way to do that because you are understanding not only the past tokens, but you are understanding the whole sentence. And when it comes to language understanding, that's actually pretty useful. So these are the differences. As you can see, the mechanism is exactly the same. These are computed exactly in the same way. The only difference is the mask of the elements, right? And that's why this matrix here is so important. So the only difference comes from the matrix. So in the causal attention, you are allowing to understand all the relationships. So you want to compute the attention scores for all the elements that J comes before Y, right? So basically, these are the tokens in the past. And for all the tokens in the future, you don't want, you are not allowed to see those values. So basically, we put here minus infinite. Why minus infinite? This seems like a kind of weird, but um, notice that all of this is inside the softmax. If you remember, the softmax have this exponential. So basically, we want this to be zero. So that's why we put minus infinite here. This is, of course, something not very formal, but at the end, this works pretty well. So these are the tokens in the future, in the past, sorry, and you're allowed to use them. So these are the tokens in the future. What I mean by future is after the token that we have in the moment, right? So, for example, this token, all the tokens that go up to here, and so on, right? And in bidirectional attention, we don't have this problem, right? So, in bidirectional attention, the matrix is just zero for all the values and all the pairs. So, essentially, in bidirectional, you don't have this masked matrix here, but it's a good way to just put the definition using the mask just to just to very easily understand the differences between those. Right, so this is essentially how the attention mechanism is computed. It's just some linear transformations of the embedding layers of the input that when you compute these values here, you are obtaining how important they are for one token to the others in the sequence. And of course, these are learnable matrix, and you achieve that goal based on the training procedure that you are using to train your model, right? And so it's kind of a, a very interesting and magical thing, to be honest. I have always been amazed by this by the mechanism because it's pretty simple to understand. I think, in my opinion, it's pretty simple to understand. What is not very simple, though, is understand why this is so powerful, right? But yeah, this is one of the reasons why transformers are so important nowadays. Okay, so these are the concept of self-attention, causal attention, and bidirectional attention. In general, the most important part here is to understand the differences between these two. Causal attention is used to predict next tokens. Bidirectional attention is used more like a language understanding, or I mean, I'm using language understanding, but this is in general contextual understanding, let's say, right? Okay, now let's move on to another topic I would like to discuss, which is really important for the paper, but it's also a very common approach when we want to train some embedding models, or we want to create some representations of some sentences or objects or whatever, right? Which is CMCSE approach. But before diving into it, I would like to discuss about contrastive learning itself, right? Contrastive learning is a really interesting way to train models. Um, so I would like to make some comments about it before going there. So let's think for a moment in classification problems, right? When you are trying to train a classification model, you are trying to predict the correct label or the correct labels, right? Depending on the problem. If you are working on regression model, you are trying to predict some continuous value, right? And basically, you are making the training of your model in a way that the model is able to predict those things. In contrasting learning, we're making the model to learn different things. We're essentially trying the model to understand relative difference, similarities between objects, relative distances, right, in some vector space. So in contrastive learning, we are trying to align some spaces. So let's think for a moment in this problem, right? So let's focus on this first figure that we have here. Notice that here we have some latent space, right? Some objects. This is a multimodal object where some text and images are inside this space, right? And if you observe that space, basically text and images are all over the place, right? We have some images here, which is this red shirt, but we have also the text of the blue sneaker and the red shirt, right? And this is basically all over the place. You just created some embedding into some space, but at this point, we don't have any kind of relationship between these objects, right? And this is very common, for example, if you just, let's think about some very easy encoder, just some mapping into some low dimensional space, you will have something like that. But essentially, we want to train a useful model. We want these objects to have some similarity between them, some relationship between them, right? So we have that the red shirt text and the red shirt image, we want them to be close, right? Because ideally, we want the representations of the same object or similar objects to be close in that new space, right? So this is previous contrastive learning, right? Or before contrastive learning. And notice that in this new space, the representation of the redshirt, which is the image, and the text of the redshirt are now close in this space, right? The distances between those two objects in this new space is smaller, right? Because they are closer now. And the blue sneaker text is now apart from these two objects because a blue sneaker is definitely not the representation of this image, right? So this is the kind of things that we want to achieve after doing contrastive learning, right? In a nutshell, contrastive learning is a way that we have to train the models so that similar items are close in that new space and different items, they should be apart, right? Basically, that's the whole idea. And if you think this is extremely important, for example, in representation problems, because we want similar objects to be close, and those kind of things, right? So even if we have multimodal embeddings, then we have different representations of the same objects to be close in the sense that the distance between them is small or the similarity is very high, right? And normally we do this through the cosine similarity, that essentially this works even if we have a different metric, like the Euclidean metric or something like that. We could use similar approaches even in that case, right? But normally we use cosine similarity or dot product, right? Which is essentially the same. Now, so let's discuss about some details, mathematical details of contrastive learning. And this is very important. I'm going to do the info in CE approach, right? And you will see just in a moment what this means. And I mention this because essentially there are different flavors of contrastive learning, right? You will see that contrastive learning has different approaches, the triple laws. So essentially you have an anchor, a positive, and a negative that you created beforehand. And there is a different way to handle those problems. But in this case, I'm going to use the influency, which under the hood is not completely different. At the end, we will have a positive sample and negative sample. The difference is the negative one is going to be created in a different way, right? So, but essentially, the idea is kind of the same. But I'm going to show you just in a moment what this term means. And by the way, I'm going to mention this because this is the approach that the SIM-CSE uses. Okay, so now let's suppose we have something like this. Let's suppose we have a data set that looks like this, right? So we have a data set of pairs of xi and xi positive, right? Meaning that for each of these pairs, this element is a similar element to this xi, right? So you could think of, for example, the xi here is the images and the xi positive is the text or something like that, right? The important part is this is something similar or related to this element that we have here. So let D be a data set, right, of pairs of an anchor and a positive example. Yeah. So I mentioned what a positive example means. In general, is something related, but we're discussing about RECSYS, right? Recommendation system. So in this space, this positive sample, positive element, normally is some kind of positive interaction to the user. So essentially, and normally, we have some kind of pairs of users and activities, right? This is not the only way, but in general, we have something like that, right? So for example, the user Carlos has performed some positive activity. And what does a positive activity means, or a positive signal means in this space? Where that depends heavily on the use case, but in general, this is some kind of click, which is some kind of implicit signal, purchases, you know, and different actions that you could perform, right? Clicks, views, whatever, right? So, for example, in Netflix, uh, you are more interested on the watches of the user, right? What the user watched. In some e-com platform, you're more interested on purchases or views or clicks or whatever. But in general, these positives means something that is a positive signal of behavior of the user, right? That's what we want. Now, let's suppose that we already have some encoder, right? Let F be an encoder. So you're taking these actions and you are passing it through the encoder, and this encoder is uh, essentially the embedding model we want to train, right? So this is, for example, the initialization of the embedding model with random weights, but you have something to work with, right? You already have encoder, so you could create some embeddings of those items, just passing it through the encoder, right? And this EI is essentially the encoded version of the XI, right? Or in other words, this is the embedding of the XI, right? Now, let's think about what we're trying to do here, right? So notice that the training goal of contrastive learning is making the similarities of these objects bigger than the similarities of these objects, meaning that you want to maximize the similarities of similar items, and you want to minimize the similarities of items that are not similar, right? That's essentially our goal, right? So let's suppose that we have a mini batch. So given a mini batch, so let's suppose we have the mini batch of our training process, right? We have a mini batch, the n, which is the same, a data set of pairs, let's say xj, xj positive, and then j1 to n. N is uh, this is not n, by the way. This is just the size, the length of our mini batch. So n is less than m. So we have this mini batch, and let's fix for a moment an I value, right? So let's fix I index, right? Because we want to compute what we are going to do. We want to compute this just for a single I, and then we will just make the generalization for all the values, right? Let's think for a moment in this I index. Let's suppose the I index is this redshift, right? So what happens if you compute the similarity of that EI with all the different values that you have in this mini batch? So let's suppose you form this list of values. So the EI dot product with the positive element 1, EI with the positive element 2, EI with 3, and so on. So EI dot EN positive, right? We're computing the similarity with all the elements in the mini batch, right? So you have a mini batch of size n, you have all the values, right? And then you are computing the similarity of your fixed I and the other elements of the mini batch, okay? Now here's the point, right? Here's the important distinction of info and C. We are gonna assume that the only related element to EI is the same EI positive. That means that all the other elements in this list that I have created are negative, right? So this is exactly the info NC hypothesis. So info NC means that the only positive to EI, or let's say to XI, the original element, is XI positive, right? And all the other elements are negative. So E equal J, they are positives. E equal different to I different to G, this is negative, right? This is very important, and in general, this is not something that you will always have. This is the unsupervised version. Because, well, it's not necessarily unsupervised because you already have some labels, but in a sense that you don't have negative. You didn't create a negative sample for the positive. There are other versions of contrastive learning where you don't have, I'm going to write this here, you don't have just a pair of anchor and positive. You have a triple of positive and negative, right? And then there is a different loss function and different things here, but in general, this is something that you might also have, right? But in this case, we won't follow that approach because in that one, you need to create the negatives using some kind of negative sampling, which is in general not a trivial problem. So anyway, but this is also very important. We are just interested in this influency uh, approach right now. So now you have this list of a bunch of similarities between your anchor and different elements, and you know that the only positive is this. Now let's call this list that we have there as the E list. Right? For a moment, let's call it list. Now, notice that if I compute, but before going there, let's call these elements. Now, let's call EY, oh, sorry, EI dot EJ positive. Let's call this the PAJ, right? Just to put in place some notation here, right? Now, let's notice that if I take this E list, if I compute the softmax of E, what you will have, right, is so you will have the softmax applied to each of those entries, and let's think for a moment how each of those entries looks like, right? So I'm gonna here. So essentially, what you're gonna have is the softmax of E in the position J, right? Because we have J different n different entries. So for the position J, this is something like the exponent of PEJ, AJ, and the sum of Kn to n, the exponential of EA dot EK positive, right? So this is the element J of the softmax, right? So all the elements of the softmax looks like this. Notice that at this point, right, after applying the softmax, you have a probability distribution, right? So this is actually, the softmax E is actually a probability distribution, right? So softmax E is a probability distribution. Why? Because that's exactly what softmax does, right? Probability distribution, right? Distribution, right? That's exactly what we want after applying softmax, right? We want to get some probability distribution of the values, right? And this J, again, right, this softmax AJ is, and that means again the entry J of the softmax E. This is the probability. We can think of this as the probability that XY positive is the positive for XI, right? This is very important because based on this assumption that we want here, this means that we want to maximize the element softmax I and minimize J if J is different to I, right? So in general, so we want, and let's call this, I call this P IJ, so yeah, let's change this by PIK, right? This is what we have here, and then, so this means that we want to maximize the softmax AI, which is the exponential PII divided K1n, the exponential of PIK, right? This is what we want to maximize, and let's call this QII, right? So QII is the entry of the softmax in the entry I. So QIJ is basically the element J of the softmax. So this is what we want to maximize, right? So in other words, you want, and here you can apply, for example, cross entropy, right? Because this is exactly the value that you want to maximize, right? So you want to maximize the probability that this happens, right? That this is the maximum value of the mini batch for that specific I, right? So you have something like the loss value for the element I is just minus the log of QII, right? You are optimizing the log probability, the minus log probability, which is something very, very common to do. And then the final loss of your mini batch is just the average, right, of all the elements in the mini batch, right? And this is essentially what you are trying to do in contrastive learning using inferencing, right? You are trying to maximize the probability that the item and the positive item in that mini batch is the greatest possible, and you are trying to minimize the other ones, right? That's extremely important, and this is the approach of inferencing, right? Now, let's talk about what we are interested in from the very beginning, right? The SIM CSE approach. And this is extremely easy to understand now that we have discussed all of this, right? So the SIM CSE, and this is the unsupervised, right? There is a supervised version, but here we are interested in the unsupervised, right? And by the way, this comes from a paper in 2022. You could check it in archive. You will find the original paper, and there are more details about this. But essentially, we're trying to, in SimCSE, we're trying to create something similar to InfoNC. As I told you, InfoNC is a supervised one in a sense that you have a positive label for each value, right? We can think of like that, but it's not exactly supervised. But let's think for a moment in that way, right? But here we don't have any kind of label, and we want to build something similar to that, right? And that's why, and that's where SimCSE comes into play, right? So let's suppose that for each xi, right? Xi here is again any kind of things. And the encoder F, again, is my embedding model. I want to train, I want to fine tune, but this is just the initialization or some pre-trained embedding that I want to fine tune further or whatever, right? But based on that, just in a given xi, let's create two different versions, right? Let's create the version xi1, which, sorry, um, yeah, the EY1, the first representation of my item, which is going to be the encoding of the xi with one dropout, right? With dropout one. And I'm going to tell you just in a moment what dropout means here. And then the second representation of this is going to be the encoder of the xi with a second dropout, right? So basically, you're creating two versions of xi and you are encoding them, right? What is a dropout? Well, it's something very simple to understand. Let's suppose we have something like this. This is a very long sentence, right? So the first dropout is just taking one piece of my sentence, one token, one word, whatever, and just mask it. It's essentially a masked problem, right? A mask learning problem, just as in the case of BERT or those kind of models, right? So this is the dropout one, for example. You are selecting some part of the sentence and you are masking it randomly, of course, right? And the second part, oh, I forgot this is a very long sentence. And then the second dropout is, for example, masking this part, right? And this is the dropout. Notice that in this point, we have created two different versions of the same base object that we have, right? This and this are not the same encoding, right? Because they are essentially encoding two different sentences in a way that one of them has one piece masked and the other one a different one. But they are the same representation of this. They are different representations of the same object, right? So in that way, these two items, these two embeddings, are the representations of the same object, meaning that they are positive samples, right? So notice that we have EY I1, EI2, sorry. And if we do this for all the values right in the mini batch, then I have E11, E21, the first version, E31, and so on, EN1. And then we have this set of the other representations, E12, E22, and so on, EN2, right? And notice that in this case, well, if I is equal to J, right, then we have EI1 and EI2. They are the same. They are positive. They're the representation of the same object. So this is positive. And if I is different to J, these are negatives because they are representation of different sentences. So the idea here is very simple, right? Using this new list that you have over here, then the idea is just let's apply info NCE in this new set of elements. And that's it, right? Because this thing that you have here, right? This thing is just the pairs of elements x I, xj, 1, 2, right? Right? And then if I is equal to j, then they are positive. If I is different to j, they are negative. And that's it. This is a very simple way to create a labeled data based on something that is not labeled at the beginning, right? We're just starting with some values, right? That's it. You have just a set of values, and you're building this data set that has the structure that we need for inferencing, right? So this is exactly what we want to do, and we will apply this in a moment in our paper. Okay. Okay. Now, let's move on to the last part of this video, and actually, it's going to be the shorter one. Because we have already discussed most of the important parts of the paper. So I'm just gonna sketch the steps that the paper follows, and then all the information that we have discussed so far is gonna be enough to understand the pieces of it, right? So let's talk about the paper, LLM2Rec, right? So essentially what the paper is trying to do is to create some latent space of the items that then we can use after that for a recommendation problem in some downstream application or whatever, right? So there are essentially three steps in the pre-training, right? There are two major, let's say, stages, right? But here in this diagram, we have three, and the authors actually mentioned that we have three different steps, but there are two main stages. So I'm gonna discuss that. So there are two, I mean, there are three, but let's say two major stages in the pre-training, right? So let's dive into the first part, right? So the first part, which is this one that is in the diagram, is something very, very simple to understand, right? So the authors created a data set mixing different data set from different contexts. So, for example, they took in sports data set, games data set, fashion data sets. They mixed them together and they created this pre-training data set, right? Then they created some sequences of the actions of the user, right? And those sequences look something like this. So for user U, we have something like TU, which is I1, I2, I3, I, and U. Each of these guys are essentially the items the user interacted with, right? Right? This is a sequential classification, the recommendation problem, at least from this stage, right? And here's something very important. The items are represented as titles, right? That is, you have the title of your items, and this sequence is essentially the concatenation of the titles of those items you have interacted with, right? So let me show you how one of those sentences look like. Well, I think I don't have the image here, but it looks like, for example, the input, the item title 1, then item title 2, so on, item title 3, title NU, and the output is basically the next output is the next element. So for example, the item, title, and u plus one, right? Something like this, right? And they created this kind of a structure, right? Just by concatenating the titles of the different items, right? So they created this. They mentioned that they are not including a lot of text or some context to not include some hidden states in the LLM. So they are just concatenating it by some comma, and that's it, right? Now, we have created this data set, and what's coming next? Basically, we fine tune, right? So then fine tune the LLM, right, which is a pre-trained LLM here. Basically, in the paper they use Qwen, sorry, but you can use any other LLM, pre-trained LLM, Llama or whatever you want to use, right? So basically, they fine-tune the LLM with causal attention, right? So this is important, with causal attention, right? Using that data set. This is a very fancy way to say just fine-tune the model using the most simpler ways of fine-tune. We just use some LoRa and just include this data set in your LLM, trying to predict. I mean, you're showing the LLM the history of actions and the output, and the model is trying to understand that, right? Using causal attention. Notice that here we are not changing anything from the LLM. We are using directly the causal attention mechanism that the LLMs already have, right? So we're not changing anything here. We're just fine-tuning the model in this way, right? Pretty simple, right? Here, there's nothing weird, just doing this. There's one reason to allow this with causal attention, and the reason for that is you're trying to predict this, right? You're trying to predict the sequence. You want the model to learn the relationship between the inputs and outputs. So, of course, you need causal attention for that, right? You want the model to understand what's coming next. And this step is essentially giving the model information about the item-item relationships, right? So I'm going to write this because it's important. So this gives the model awareness of item-item relationships, right? Because the model is trying to understand what's coming after this item, after this history, right? This is pretty simple. I've seen approaches that actually stop here, that this is kind of, the awareness they want the model to have, but the paper is going a step forward, right? So they're trying to do more than this. This is just the first step. Now, let's go to the second step, right? We have something very interesting here. Here we are trying to model this at the item level. So here we have item level modeling. Notice that this is modeling item-item relationships, right? But then we want the model to understand at the item level what are the relationship of the items and the titles, right? So we have two major steps here in this first part. The first sub-step is now we are going to change something. Now, here we are going to change the causal attention mechanism to bidirectional attention. So here we are allowing bidirectional attention in the model, and then train using masked next token prediction. In other words, you already have this fine-tuned LLM, right? This LLM has new weights, right? Updated weights, the result of that fine tuning. And then that LM that you have from this stage is going to be used sequentially to perform this, right? So essentially, you are changing the causal attention of that LM, and you are including a new step of training using mask next token prediction. What's mask next token prediction? Well, essentially, you have this um, sequence, right? This is the sequence of some item, right? This is very important. This is the sequence of tokens of the representation of the item. This is not the sequence of titles, right? Of items that we have here. These are tokens of the item, right? Notice that that's why we have this name, right? We are doing item level modeling. Here we are not concatenating items from different users. We are just using the representation of each item to perform this fine tuning, right? So these are the tokens, and next masking prediction is what you can imagine or you know. It's basically masking these. Just masking, right? Just changing this by a new token that represents the masking. And what the model is trying to do is gonna predict what's this next token, right? But the important point here is we have allowed bidirectional attention. So the model is gonna use not only the previous tokens, but will also use tokens from the future, right? So it's gonna use this. And why is this correct? I mean, why is this acceptable? Because we want context understanding, right? Up to this point, we don't want to predict what's coming next in the title. We want the model to understand all the relationships in this item representation, right? Which is not the case that we had here. Here we wanted the model to understand these relationships. In this case, we want to have some context awareness. So that's why allowing bidirectional attention is it's a very nice idea, right? Because at the end, this is, for example, what encoders models like BERT do, right? They allow bidirectional attention so they can understand the contextual understanding of the language or the things that we're trying to do, right? We are not trying to predict next token. We're just trying to understand um, understand the context, right? So this is the first part. Now, notice that up to this point, again, even after this, we have an LLM, right? We have an LLM that basically is trying to predict next token. But the whole point about this, we don't want only the LLM. We have the representation of the items. We have some embedding of the item, right? So in this second part, we're gonna get the embeddings, right? So this second part is get the embeddings from the fine-tune, the two-stage, right? Fine-tune LLM, right? Averaging the last hidden layers of the tokens, meaning that the representation of the tokens from the LLM of the item. In other words, if I have the title here, TI, and then we have all the tokens of that, right? This is the length of the title. These are the tokens again, right? So these are the tokens of the title. And if we say that EIJ is the last hidden layer of token TIJ, then the final representation of the title is just the average, right, of those representations, right? And this is how we get the embedding, right? By the way, this procedure is not completely new. I mean, this is not some kind of breakthrough from this paper. Actually, this is exactly what this paper called LLM2Rec does, right? This is other. This is another paper. I think this is a paper from early 2024. If I'm not mistaken, probably late 2023 or something like that. But this is a paper between 2024 2023, and actually the procedure is very similar, right? This proposes a way to create encoders from LLMs, and the approach is very similar to this. They allow bidirectional attention. They get the final layer using something like this, right? So it's pretty similar to this, and actually the name, this is not coincidence, right? I mean, LLM2Rec is inspired by LLM2Rec, but LLM2Rec is a novel paper in the sense that they are using this for recommendation tests, and they are showing that actually this is a pretty strong approach when it comes to recommendations. So that's why this is a very nice paper, even though the procedure is very similar to this. Okay, now the last part and the final part of all of this is just, okay, we have already two stages of fine tuning, right? But there is one, and there is a third step of fine tuning. And this is very simple. This is again for item level fine tuning. This is just apply sim CSE using the encoder obtained in step 2.2, right? Notice that this is the encoder of the final pipeline of fine-tuning here. And in the step 2.3, basically apply SimCSE in a way we saw using this encoder, and we are going to apply this, of course, at the item level, right? So apply this. Let's put this at an item level. So you have all your items, and you are going to build the pairs in this way, right? Applying SimCSE, and then you are going to perform that contrastive learning approach, right? So notice that at the end, we have something like three different steps, right? You start with some LLM, let's say pre-trained LLM. Then the first step is fine-tune using causal attention. Then the second step is item level mask next token prediction. And then the third part is again item level sim CSE. And this outputs the encoder. And then, of course, this encoder can be used in downstream applications, so you could use this as an embedding model, um, in some applications that you have after that, right? So, for example, using that as the initial representation of some items, and then doing that, or even that, using this just as a plain embedding thing for an item collaborative filtering or something. But at the end, this is the output, right? The final encoder of this is what we are really interested in. And the paper also mentions some adapter to downstream applications, but I think this is the backbone of the model, right? Now, how does this work? I mean, is this actually all the metrics they show in the paper um, are very strong metrics for recommendation problems. They outperform some GRU for REC, for example, which are recurrent neural networks for recommendation problems. So this is actually a very strong recommendation model. And if you want to see some metrics, you could check the embedding and just I will paste the link for the embedding in the comments section. So yeah, this is actually a pretty nice paper. There are a lot of concepts. It shows really strong results, which means this is very promising when we want to work on recommendation systems. And actually, the pipeline is not very hard to implement. At the end, this is heavily inspired in LLM2Rec, and they have published the source code. So yeah, that's everything I wanted to show you today. Thank you for watching.